Yep. Which button? Oh. All right. Resuming. Welcome everybody. Those of you who weren't there in person for SLT High 134 subset -3 get to enjoy the third but final SLT High, which is about the learning coefficient, also known as the RLCT. Here are the references I'll be referring to throughout the talk. I'll post the slides as usual on Discord, Green Book, WBASC papers had a mention. There's a paper that wrote with Susan and some other colleagues, Shaway's thesis, and some linealogic stuff, since people seem to be curious about that. I'll tie that in at the end. Okay, just to recap what the learning coefficient is, why we care about it. So the free energy formula is the main equation. It expresses the free energy in terms of a potential energy, as we've learned over the last 3 days, LNW0, and the learning coefficient lambda. I won't explain what LNW0 and what this formula is for, because we've gone through that in previous SLT highs. But this is a formula we've used to talk about phases and phase transitions. And this term is easy to understand, right? This has something to do with error, but the second term is somewhat mysterious, right? So I'm not going to dwell on the definition, right? Because you can look up the definition. There are several definitions. It's a polar for zeta function. I'll give you that definition. It comes from resolution. If we had 3 weeks, I would teach you the algebraic geometry you need to understand canonical divisors and all that, but I'm not going to talk about that. So I'm going to try and give you some idea of how I think about lambda and lambda log n in terms that fit into a lecture here. It'll only be part of the story. So it's a very interesting, deep quantity. I'm going to sort of interchangeably refer to lambda as either the learning coefficient of the RLCT. The reason for that I'll address in a second. They're kind of the same thing under a mild condition. And just for simplicity, I'm going to consider only the realized case, in which case we actually get not zero. What should that be? S. Yeah, good. Okay. In a case where we can actually K of W0 can be 0, we have a model which actually realizes the truth. The story is no different in the general case, which is the setting we've talked about phase and phase transition. So you can read everything I say as being about the free energy of a phase, not necessarily a phase that belongs to the set of true parameters, but it just simplifies matters to consider the case. This is W0, so actually K is 0. Otherwise, just go to replace all the K's everywhere by K. Jesus, okay. Let's fix this too. What should that be? Replace L by L minus L. Okay, so here's an outline. So I'm going to give you a reminder of the definition. I'm going to give you some simple examples and some of the basic rules that you use to compute RLCTs. I'll make a brief comment about sort of how you think about symmetry in the context of RLCTs. Sort of go through how we estimate the RLCT in practice. I think Edmund covered this, but it's worth repeating perhaps. And say something about the relationship between the learning coefficient and entropy. There's been some discussions over the past couple of days about the sort of role of description length or Kolmogorov complexity as a way of thinking about which parameters are preferred by the posterior. However, we haven't really, when there's an intuition about lambda that's sort of been missing throughout the discussions. Lambda is really not a description length. It's similar in some respects. So in the minimally singular case, that's a reasonable way of thinking about it. But there's sort of an extra twist, which is one of the things that I want to emphasize. And then there's just some kind of storyline at the end. Okay, so the definition. We suppose given a triple P, Q, phi, usual situation, satisfying the fundamental conditions, the KL divergence is that. Then we can consider the zeta function. So that it's not holomorphic, but it can be analytically continued to a meromorphic function whose poles are real, negative, and rational. And the learning coefficient is such that minus lambda is the largest pole. So the pole furthest to the right on the real axis, its multiplicity is m. Now, I realize people see this definition and it just looks like mumbo jumbo. It's here to give you a precise definition. I kind of sort of promised I was going to go through asymptotic analysis and Mellin transforms, but I could not find a way of fitting that into 1/4 of this lecture and actually communicating intuition. So that's a job for another day. Sorry. So we won't dwell on this. I just want to make this point that the definition of the RLCT doesn't involve the prior. All right. The RLCT is of a function. It's the RLCT of K. It's defined by resolving K, putting it into normal crossing form. But the zeta function involves the prior. So in principle, they're different things. The learning coefficient is a pole, minus of a pole. The RLCT is some geometric quantity. But as long as the prior is positive at the place where the RLCT is minimized, it doesn't matter for the asymptotics. It doesn't matter for the pole. And so they're the same quantity. So it's like, if you choose the Jeffreys prior or something like that, then these two quantities would be different, but that's sort of technical. So it's for this talk, I'm just going to conflate learning coefficient and RLCT. But if you sort of notice Watanabe using one and sometimes the other, this is the reason. Okay, they're sort of basically the same thing in the cases you probably care about, unless you're Alexander and in love with the Jeffreys prior. Okay. Shelley's thesis is an excellent reference for some of these basics about RLCTs. The real log canonical threshold is much less studied than the log canonical threshold, which is a complex algebraic geometry quantity, very well studied. The RLCT much less so. They're not the same thing, but that's, again, sort of veering off into deep waters to get into that. Okay. So the zeta function had an integral of a W in it. You can restrict that integral. If you do, you'll get the learning coefficient or RLCT of some subset. Or you can do it at a point by taking a point in W or some closed set and taking a neighborhood. So that gives us a local RLCT. So the local RLCT is the thing you get by computing, well, the pole of that integral, if you just restrict it to a neighborhood of the point. Okay.
The neighborhood is inside the ambience.
That's right. Yeah. So the global RLCT is the infimum of all the local RLCTs. Okay, so the example in which the RLCT is trivial to compute is the one where you have, K is non-negative, so it looks like a product in normal crossing form of even powers. Right? 1 is supposed to be a subscript. So then lambda is the minimum over 1 over 2kj. Putting that into normal crossing form, as we know, is what the resolution of singularities does for us. Okay, so there are sort of 2 steps involved in computing RLCTs for non-trivial models, like one hidden layer tan H. The first is you start with an analytic KL divergence. You find a polynomial which bounds above and below KL divergence in this way. H is a polynomial. In general, if you have such bounds, then you have the same learning coefficient, same RLCT for H and K. So given the analytic function K and a polynomial H, you compute the RLCT of H. You do that by resolution, which you sort of algorithmic once you've, it works for any analytic function, but it's something you can actually carry out in practice if you are very, very patient for a polynomial. Okay, and that's, sort of one of the hard corners if you're actually studying a specific model and want to theoretically compute the RLCT. It's non-trivial. Yeah, this is a place where theoretical progress would be desirable, and that probably will happen. So the present state of affairs is a bit kind of primitive, but that's where we are. Don't worry about this, just assume you sort of keep the prior fixed. Consider 2 models on the same parameter space, same prior, or satisfying this. If one KL divergence is less than the other, imagine W as being the optimal parameter, or the or a true parameter, at which the global RLCT is minimized as their true parameters. Sorry, okay. If you have this inequality for all W in some neighborhood of the set of true parameters, then the RLCTs is related like this. So inequalities on the KL divergence, you get inequalities in the other direction for the RLCTs. So these are the basic recipes you should have in mind if you're thinking about RLCTs. Okay. This is also useful. If your KL divergence splits as a sum of two pieces, one of which depends on some subset of the parameters and another which depends on the other set of parameters, and the prior decomposes and the RLCT is additive. Okay, so it's kind of extensive. Now this I think we're all aware of by now. The dimension of the parameter space is D, when you can upper bound on the RLCT. And if K local coordinates looks like a sum of squares but not full, so D prime is less than or equal to D, then the RLCT, this is near P, and the local RLCT of P is bounded above by D prime on 2. So roughly you should speak, so this says that there are D minus, this is flat in D minus D prime directions, right? So there are D prime normal directions for the set of true parameters, and roughly speaking, you should think of for every normal direction, you get 1/2.
I'm just curious, so in bounding RLCT by D on 2, take any right?
Yes.
Yes. So then if K is, let's say, a sum of, like, say, any, why is it UI squared? Why not any power series that's up to D prime with bounded by D prime on 2? Why does it have to be UI squared?
Oh, why UI squared?
Yeah.
Why not a higher power?
Yeah, or like a different.
Oh yeah. If it was a sum of higher powers, then it would be bounded above by the 2, 1. Yeah, that'll follow from the 1. That follows from this rule and this rule, right? Yeah, because if you have a sum of powers, you could deduce this from this and this, right? At least if you use them locally. Because this is a sum of polynomials of distinct variables. So the RLCT of this must be the sum of the RLCTs of these. The RLCT of U squared is 1/2.
But what about the prior condition?
Yeah.
What about it?
The product.
Is it just assuming some niceness on the prior that treats direction?
Yeah, you need less than that, but it's like, I don't know a clean way of stating the actual condition. You mean down here? Yeah, that's true. I mean, the prior could mess that up.
Can the prior mess up that dot point?
This dot point, as long as it's positive, no.
If you're getting the bottom bullet point from the additive condition and the normal crossing condition, why do you get the less than or equal rather than just equal?
I think precisely because the prior need not be a product.
Oh, okay, with the prior.
I think that you bound the prior by something.
Yeah, I mean, this is stronger than this, right? So, okay, if it was like, yeah, if it looked like this in local coordinates at every P, then this would, well, no, okay, yeah, this is actually equal. You're right.
Should be.
It's equal. Yeah. Thanks.
Okay.
Any other questions about this one?
What if you had a sum of quartic deviations in local coordinates? Would you then, is there an intuition where you would just add a quarter for each of them and so you get D prime on 4?
Yeah, that's right. Yeah, it just follows from that.
Okay.
Yeah.
Do you have any information on the degree of H, U and K?
In the inequality.
Yeah.
I mean, so this holds around, so you need this around the 0 set of K, in which case they're related by a multiple of a non-zero analytic function. So in the power series expansion, they'll have the same lowest degree terms. But you're asking about the polynomial degree.
Yeah.
Yeah, that's very difficult to say. Yeah, so if you look at the form of H for one hidden layer tan H, you'll sort of see that it depends. The degree depends on the number of hidden nodes, for example. Yeah, so I don't know a simple way of saying what the degree is. Yeah, it's an interesting question.
When it was even, many number of variables could be composed as some squares and automatically get this sound. So, yeah,
Which one? This
the sum of squares. So it's unbalanced. Oh no, yes.
Not sure what you're saying. Maybe you can tell me after. Okay, so for example, this is an AN surface singularity. You just compute the RLCT by adding up their indistinct variables, just add up the reciprocals. Okay, so not so hard to compute. As long as they're sums of indistinct variables. Once it gets more complicated, you'll have to resolve things. Okay, so some sort of general comments. I mean, in any particular example, it might be difficult to see whether this is sort of manifesting itself or not, but this is SLT high, right? So I want to give you some intuitions for how to think about these things as a part of a package of trying to reason about how this affects learning systems. And this is an interesting one that's actually come up in some conversations over the past week. So it's the role of symmetry. So I guess we all sort of have a general intuition that the more symmetric something is, the less bits it might take to specify it, and therefore its complexity might be low, and therefore that solution might be preferred. Okay, so you can realize that in this context in the following way. So suppose there's a Lie group G, that just means a group whose elements form a manifold, so you can smoothly move around inside the group. In particular, near the identity of the group, there's a small patch where you can move around, and you can ask how many distinct linear directions are there at that point, the dimension of the tangent space, the dimension of the manifold. That's dim G.
You're assuming that P is fixed by the action of the group. It's a fixed point.
Yeah, I didn't say that.
You didn't say that.
Well, let me say what I've got written there, and then I'll come back to your question. So if G is acting on W in a neighborhood of P, yeah, that's right. Yeah.
P is a fixed point.
No.
It doesn't matter.
No, it shouldn't be a fixed point.
Okay.
I want K to be G invariant. So you could think of, so suppose this is the KL divergence of a neural network that is using the weights in a way that depends on dot products, say dot products of columns, like in toy models of superposition. Right? Then that means that if you act with the orthogonal group on the columns of your weight matrix, you get the same loss, you get the same KL divergence, right? So that's a symmetry of your parameter function map, and therefore a symmetry of your KL divergence. That's what I mean by K being G invariant. And if P is not a fixed point, so that all those infinitesimal directions of the identity in the group actually send you away from the parameter P, then that means that these dim G directions in your group, when you act on your parameter, create generically dim G directions in parameter space, and those will drop. Those are directions in the space of true parameters, right? Generically speaking, we think of the RLCT as being giving you 1/2 for each normal direction. The more directions in the space of true parameters, the less normal directions, so the lower the RLCT. Okay, so you'll get an upper bound of not D on 2, but D minus the dimension of G, because you sort of have dim G, more directions in the space of true parameters. Okay, in your particular case, and who knows whether that lower bound is actually like affecting the actual RLCT, it's only an upper bound. So this is not telling me exactly what's going to happen, but it's an intuition about how symmetry might affect this quantity. So roughly speaking, the more symmetry that you have, the lower the RLCT. So all else being equal, more symmetric solutions are preferred, given the free energy formula. So yeah, we sort of talked in SLT high 1 about type A and type B phase transitions. If you remember, these were the ones that we sort of thought of perhaps happening at the end of training or near the end of training, where the energy is very low, perhaps 0, and the RLCT is being decreased. Potentially, you could find examples where that decrease in the RLCT corresponds to finding parameters that implement the same function, but in a more symmetric way. I have no idea if there are examples like that, but that would be interesting. So a word on RLCT estimation. Edmund, you covered this in your talk, right?
Very quickly at the end.
then let me cover it also very quickly. Okay, so this is the basis for our LCT estimation. There's a variety of ways of doing it, and we'll see more in the future, I'm sure. I'll comment on the theory behind it, how that maps into practice, and how scalable we think that might be. The WBIC paper, the WBIC is an estimate of the free energy, which doesn't depend on knowing the true distribution. So what Watanabe proves is that if you take the expectation over the posterior of NLNW at a specific inverse temperature, 1 over log n, then this is giving you an estimate of NLNW0 plus lambda log n, so the free energy. So this thing on the left at this particular inverse temperature is the free energy.
Roughly,
Roughly.
large
Large
N.
n, yeah. Okay, so how do we, that means we need to know, if we want to know lambda, we need to know these two quantities, right? So this is an expectation of the posterior. So of course we have to approximate sampling from that. And we need to know this quantity. Well, Ln we know how to compute, but that doesn't depend on the true distribution. But W0, this is the same conditions as in the free energy formula. So this needs to be an optimal parameter. So we need to have some knowledge of LNW0 of an optimal parameter. So that's something else we need to assume. But dealing with the left-hand side first, we can take a data set and then approximately sample from the Bayesian posterior by a variety of methods, and then just rearrange that formula to get an estimated. All right. That was exciting. We can get an estimated lambda hat. Right? So this is the EW NLNW. This, you could try and get something like that by, if you're doing this in some neighborhood of a parameter, you want to know lambda hat of a phase, for example, you might take a parameter that you think is in that phase and do gradient descent with some kind of decaying learning schedule to try and find a local minima nearby.
What's up, both?
Yeah, I just mean SGD, but like decaying learning rate, maybe with the prior.
SGD, but like don't go too far away.
Yeah, something. Yeah.
The WP is just the free energy formula without the higher order.
That's one way to think about it. Yeah. Yeah. So the free energy is there's an OP log n. Yeah. Yeah.
This is not how Watanabe actually wants us to estimate lambda hat in this paper, right?
That's right. There's another method in the
This is
paper.
like I would only do this. This is cheap, but Watanabe would advocate that you try multiple inverse temperatures and then you do a linear regression, because that inverse temperature beta, instead of 1 on log n, it would show up on the other side, and then you could basically learn the lambda by doing these squares.
Yes.
But that's expensive.
Yeah, that's what we did first.
But that is still what Edmund did in his pretty graphs.
Yeah, that's right.
Yeah, that is still the better estimate.
So that's one way that's described in the WBIC paper. This is the second one. Yeah.
So the other quantities like the singular fluctuation and stuff, do those just require totally separate kind of
You get it
method?
for free once you get these posterior samples.
Yeah.
You can estimate that. No additional computation.
Yeah, so basically the only tricky thing here is getting samples from the posterior. So you can do that in a number of ways. One is Markov chain Monte Carlo, which, as we're aware, is slow, only works in low dimensions, but is accurate. Or things like SGLD, stochastic gradient length given descent, which is fast, scalable as SGD. People seem to believe there's theoretical reasons to think it's sampling from the Bayesian posterior. I don't think, if by that you mean you read the paper and you were convinced by what's in that paper, then you have not been convinced. There may be other reasons. Someone can educate me better, but that paper doesn't have a reason. That doesn't mean in practice it isn't doing something useful, right? So, but it's more like Wild West, right? Don't think that somebody's got your back.
Locally fine.
Locally fine, yeah.
Yeah.
I think believing in this is kind of a proxy belief that SGD is the Bayesian posterior. So if you believe that, then this is even better. but it is scalable. So, depending on what you want, this is like something to try, right?
Let's say, so there's also a difference between the Bayesian setting that singular learning theory describes and SGD. So if there is a difference between sampling from the posterior and SGLD, and do you think there's like you use SGLD to get a lambda hat? Do you think that's like the one that you would want if you were doing a singular learning theory of SGLD, or is that just?
Those are tricky theoretical questions, actually, I think. Yeah. I mean, you can say that, but like,
There's no reason to believe that the way that it may be misaligned is the same as the way that SGD may be misaligned.
Susan should be the one to answer that.
I think it's fine to redo everything, but for like a pseudo Bayesian posterior. So
Yeah.
the SGLD, the stationary distribution, it looks very similar to a posterior distribution, right? But instead of like e to the negative ln, right? It's not ln, it's something else based on the data, probably defined by a loss function. It's very, very similar. So I think what you get out of this by using SGLT is that lambda hat is it's for not pure Bayesian learning,
But that's what we want, right?
but that gives posterior is not exactly the stationary distribution of SGD. There's still a little gap there, but the gap is smaller. That's sorry.
No, it's okay. It's just a good comment. I should record. Any other quick? Yeah.
Yeah, so if you were to do like full batch gradient descent with noise, is that just MCMC or is that the third thing?
That's sort of Langevin. So that's what this is interpolating. So this is sort of interpolating between Langevin descent and SGD.
Okay, so that's SGD plus.
Yeah, so there's,
Yeah.
it's actually
No
I mean,
noise.
the story is that like early on it's SGD because then you escape local minima, and later on it's Langevin, so then you're sampling from the posterior. That's the story of the paper.
I see. But theoretically, like if you were already like at the minima, you could just, and you know, well, I guess there's problems.
If you're already at the minima, you probably don't need the SGD part, and you just do that. What you said.
Yeah, I guess it's the GPU or like memory and stuff is probably bigger.
I guess I hope like the status of this is cleaned up at some point, but I don't think it's a big limitation for now to just go and try and measure it in a bunch of things. Yeah.
Can you give some introduction about what the descent is?
Oh, okay. So this is just so it's just gradient descent plus Gaussian noise. So just full batch gradient descent.
Is it full batch?
Not the stochastic,
No,
Yeah,
SGD.
just
Oh, sorry, I didn't hear the question.
just Langevin descent.
Yeah, not SGLD. That's got SGD in it as well.
So SGLD is just SGD plus Gaussian noise.
Mixed in a very particular way, yeah. With like some decaying, like interpolation term between. Okay. All right, so here's sort of the connection between lambda and entropy. And basically, I just want to sound a few notes of caution here. So this is a story that's in Liam's blog posts to some extent, and in some of the documents we've written to an extent. So this is a formula for the RLCT you'll find in chapter 7 of the Grey Book. It's expressing it in terms of volumes. I think this is the easiest definition, if you like, of the RLCT to understand. So VT is the volume of the set of parameters that are almost true, right? VT. So it's the integral of the prior over the set where KW is less than T. So then you can prove that if you take that quantity and then you take these ratios, the logarithm divided by log A, take the limit, you get the RLCT. So this is, I mean, the reason this is true is that this is the integral of the state density function, right? Because if you want all the parameters of energy less than T, you should integrate the state density function over all those level sets. The state density function, as Edmund has explained, is related by these transforms to the zeta function and the other quantities we care about. And so then this lambda shows up. But Basically, most of this is just kind of an obvious way of unpacking an exponent once you sort of see it. So let's go back to the case where KW was a sum of squares, not a full sum of squares. So D prime is potentially less than D. Then if you do this integral, you're just computing the volume of a sphere in D prime directions, and then the prior does something in the other directions. Just kind of assume it's integrable and the prior factors some way. So this just gets you a constant times T to the D prime on 2 for that volume. Then what is this? Yeah.
Where does the A come from?
Oh, the A is made up. Yeah, pick any A that's not equal to 1, greater than 0. Yeah. It's just to extract the exponent, right? So if you look at this ratio, the A's cancel out. The T's cancel out. Sorry. The T's cancel out. You take a logarithm and then you cancel out the log A, right? So it really didn't matter what the log A was. What you're doing is you're seeing how fast does the volume grow, right? If you allow more error in your parameter, how much more volume do you get? Yeah.
So are you basically like, if you kind of take like a presumption that like you don't know anything about singular learning theory and you have no idea that this is related to your SLT, you're just taking this limit.
Yeah.
Because is this sort of implicitly making a presumption that the volume scales exponentially like that, and you sort of like you need singular learning theory in order to get that fact?
Yeah, basically to see the scaling behavior, which isn't actually this. There's also a logarithm term here, so I'm cheating a bit. So this is assuming the multiplicity is 1. Well, okay, in this case. I'll get to that in a minute, the general case. In this case, you don't need any singular learning theory to do this integral, obviously, but in general, to know that this had the form T to some exponent, there's actually a logarithm term. Yeah, you need to understand the state density function and these integral transforms, and I don't know a way of doing that apart from resolving things. Yeah, so you'd sort of, probably that's how Watanabe ended up. Well, one of the ways you could end up thinking about this.
If it doesn't factor, I guess the effect is, somehow when I stare at this V of T, it feels like the prior should play a greater role in determining lambda.
Not as T goes to 0. So I mean the asymptotic formula, as long as the prior is positive along the 0 set of K, we know what the asymptotic form of this volume is. So I agree that if you do it by hand, it looks like the prior might matter, but yeah, so I'm saying this just for this silly little example. It's not actually a requirement. Okay, so there's the actual formula plus a lower order term. Right, so it's a constant times T to the lambda. Lambda is the RLCT of the model. And then there's a term here that depends on the multiplicity. I'll just assume it's a simple pole. So it looks like this, because I just want you to sort of have the intuition for what this increase in volume thing is doing. Okay, so let's ask the question, how many bits does it take to specify a true parameter? Well, specifying a true parameter means maybe specifying a real number to infinitely many decimal places. So that is not what we want to ask. But we can ask the question of like specifying it to some error. And I know like 99% of you eat information theory for breakfast, but just in case you don't, here's how you would think about specifying something in a space of parameters in terms of bits. So take the parameter space, that's W, and the intuition I'm about to give you is sort of for regular models. So for a regular model, there's the true parameter. It takes me 1 bit to decide that it's on the right-hand side of that divide, another bit to specify that it's on the top half of that box, another bit, etc. Right? So each bit you spend, you're halving successively to find the true parameter up to some resolution, right? You choose the resolution, that tells you how many bits you need. Okay, what about the singular case? Well, we have a bunch of questions. The first is, okay, I could play the same game. I need to specify a true parameter. I halve, wait. Well, this is the set of true parameters. Like, which half do I choose? This true parameter is in both halves. Okay, maybe I choose that half. Well, there's not one true parameter. So what is it? do I mean specify our true parameter, or the true parameter, or a particular true parameter? I have to ask number of bits relative to who and what coordinates, right? Of course, the number of bits it takes to specify also sort of depends, on the coordinate system you're using. That's a constant, so we don't usually worry about it. So that's not an issue, but there is a difference between the kind of information that's tied up in the RLCT, which is about what you might call local bits, and more global bits. Yeah, I'm going to focus on the local bits. So global bits, I'll come back to in a minute, but you might think about that as, okay, you've got some picture of the whole parameter space W. You need to spend some bits in order to zoom in on some neighborhood of one of these parameters that is the deepest singularity on W0. And then when you're in that neighborhood, maybe you spend more bits to get a more resolved parameter. That's not a question. So some of those bits are sort of getting you into the neighborhood in which, like, once you're in that neighborhood, the asymptotics hold. This is asymptotic as t goes to 0. So you can't use this globally, right? It doesn't make any sense. So you have to get close enough for the asymptotics to work. And those are bits that just haven't, the theory doesn't say anything about them, right? Then when you're really close, the asymptotics start to give you some idea of the number of bits you're spending. That's what I mean by the division between global and local. You could also ask, well, let me just say like what the neighborhood of the set of true parameters is sort of globally in the whole space, the ratio of those volumes. Again, that's not something that's easy to compute, right? You can go look up volumes of tubes and think about that, but that isn't what the RLCT is talking about either. Okay, so we're going to think about the number of bits it takes sort of locally to specify a true parameter up to some error. And we have in mind a particular true parameter, which might say is the deepest. So it would be the deepest singularity, the one where the RLCT is minimal on the set of true parameters. Here's the problem formulation clear. Okay. So here's an example of the global bits, right? It came up in SLT high 4. So in the toy models of superposition, let's say we start in a neighborhood of a parameter that looks like this. I won't remind you what the model looks like, except to say that this is n equals 2, n equals 5. So there's a 2 by 5 matrix. These are diagrams of the columns. They're local minima of some potential. Moving from here to here is moving from one local minima to a lower local minima. And then from here, there are 3 ways you could go to a local minima. And then from each of these, there's a bunch of further places you could go. So you need information to specify which one you're choosing, right? There's a choice of 1 out of 3 at this step, and there's a choice of 1 out of 4, so 2 bits to go from here to here. The asymptotics don't see that at all. That's completely invisible, right? The RLCT has nothing to do with those bits. Okay. In fact, this is a minimally singular parameter, so the RLCT here is easy to compute. But sort of, if you're thinking about the information required to specify that parameter, you sort of have to think about the difference between specifying just this one versus somehow pulling out all the true parameters up to some error from the parameter space, and you have to think about these bits. But that's a story for another time. Yeah.
Basic question. It's minimally singular. That's because this is a linear model. So,
No, because you can look at the potential and compute its Hessian.
okay. It just happens to have that quadratic versus.
Yeah.
Right. Yeah.
Okay, so let's zoom in and do a little calculation. Well, how many bits does it take to specify a parameter where kW is less than 1 on n? Well, it's negative log base 2, the volume of the set of parameters where this is true, which is V 1 on n, divided by V. V is the volume of some region, which is sort of maybe where you ended up after you spent some bits to get near to this particular parameter. Okay, so I'm not modeling the V, that's just some other bits, some global bits perhaps. Okay, so, all right, substitute in the formula for V. All right, so I'm putting 1 on n in there, then I get lambda log 2n plus log 2V.
Where did the C go?
Oh yeah, plus, yeah, thank you, plus a constant from the C. Yeah. Yeah, actually, that's kind of interesting. So that's actually to do with the prior. So that deserves to be there, and it's probably interesting. Yeah, I'm not going to talk about it, but it's real and it's probably meaningful. Yeah. So this is a kind of local entropy to which we can add a global entropy of specifying V within W.
So what is so V is like, what do you mean by represent the current state of knowledge?
Well, V is this box, if you like, sitting inside the whole parameter space. So how many bits does it take to
Specify V.
this box within W?
Right, okay.
All right. So
But it's different from VT.
yeah, bad choice of word. So to specify a parameter with kW less than 1 on n, you need lambda log n plus log 2 log v bits, up to the difference between log n and log base 2n. That's the stochastic complexity product of the learning coefficient and log n. Okay, so this is an entropy interpretation for that. So you could think about it this way. Suppose you know a region of parameters in which kW is less than n, and you want to improve to a region of parameters where kW is less than 1 on n, then that's this ratio. That's approximately, for large n, lambda on n, which you might remember is the Bayesian generalization error, right? So you can think of the generalization error as being kind of the cost in bits of improving your knowledge of a true parameter by the difference between from 1 on n to 1 on n plus 1. And that's, I presume, why Watanabe is calling this the learning coefficient, right? So it controls the exchange rate between entropy generated, which would be energy and heat that you are sort of generating by the learning process, perhaps, and decrease in error. Okay.
This technology is really old.
Yeah, that's true.
Well received.
That's true. Yeah. So
Which terminology? The learning coefficient?
Yeah, like these whole mechanics people. All of this in the settings.
Okay, and they didn't know maybe the link to algebraic geometry.
No, they don't.
okay, so the larger the learning coefficient, the more you have to spend to improve performance.
So is it like if the lambda is 1 over n, I need n bits to improve the error in how much?
So to improve the error from 1 on n to 1 on n plus 1, you need lambda on n bits. So as n increases, you need less and less. But the rate at which it decreases is controlled by the RLCT.
And 1 over n to 1 over n, that's in the scale.
Yeah.
Yeah.
So yeah, I hope that's like useful as a way of thinking about it. So I would sort of, I mean, this is basically what the volume presentation says, right? That formula, once you just sort of unpack it, it says this. So this is a way of thinking about what the lambda means.
So double order precision takes constant number bits. Everything's logs. So.
Yeah, that's true. Yeah. So by the way, when you integrate this, right, which is sort of related to your question, yeah, if you integrate it, you get the free energy. Yeah, so it's one way of thinking about that. If you're in a realizable model, so that other term there is 0. Okay, but I want to emphasize that it's not a good idea to make loose sort of conceptual associations between what the RLCT is talking about, which is a local and asymptotic measure of this entropy, with like kind of more global quantities, like regions of parameter space, right? The RLCT is fundamentally a very local quantity. Okay, yes, I'm moving on to another topic. Yeah.
Yes. So this is specifying a particular true parameter, namely the one with the lowest local RLCT.
Correct.
But is it fair to say that if you want to specify the set of true parameters, given that your the person you're communicating with knows something about the model, you have a choice of which parameter to send them in that set, right? So you could, this might be the
this is a
easiest
lower
one.
bound. No, I mean, this is a lower bound on the other RLCTs will be larger, so you'll have to spend more bits to specify something.
Okay, so yeah, that's what I'm gonna say, is if you're in the situation where you want to pick, then this is the smart choice
Yes.
of which one to send. If you just want to communicate an arbitrary parameter in that set, okay.
So you're emphasizing it's a local asymptotic quantity, but it's also the case that it's like locally constant, right, along a variety,
Mhm.
right?
Sorry, could you unpack that? Either of you?
Well, it's a rational number, so it can't vary continuously.
Uh-huh.
So it will sort of,
And yeah, so there's going to be some curve or some plane or something like that where that it's constant on, right?
Yeah. that's right. So this, I mean, this sort of related. So this is talking about at the point of deepest singularity. And we're talking sort of very locally to that. But the point Nathaniel's making is that RLCT holds perhaps not only at that point. Right?
I'm a little bit confused. Maybe this is, so you have singularity, it looks like this. Is the RLCT different at the point versus near the point?
Yes.
And so in what sense is it locally constant?
Well, so so in that case, like, then it might be just locally constant on the dimension 0 thing,
Okay, sure.
but along that
Along the
line,
line,
then
that's
it's gonna be locally constant.
You want to say this semi-continuous, so
Yeah.
not
We can talk about the precise meaning of locally constant.
not
Okay.
semi-continuous.
Thanks.
It's a
You have
rank
another
of a
question? No.
sheaf.
All right.
So semi-continuous.
Okay, it's tempting to think about lambda as being related to description length because that's the main way we think about complexity of objects. But I don't think this is actually a good analogy. It's reasonable in the regular case, it's reasonable in the minimally singular case, but in general, it is not a good way of thinking about what lambda is talking about. And so I want to really put my finger very precisely on the difference between description length, counting the number of okay, I guess that seems to contradict my previous slide a little bit, but I'll explain why. Description length sort of meaning not, so counting the number of
Degrees of freedom.
yeah, degrees of freedom, right? Yeah, so the point I want to make is that, okay, I think I'm phrasing this badly now that I look at it. The point I want to make is why, so the question you might have, seeing the minimally singular case and seeing the regular case, is why do some parameters count for less than others, right? Some parameters count for a half, others count for significantly less than a half, and what determines the difference conceptually. And you can look at the examples, you can do the blow-ups, but what's a kind of conceptual reason for this distinction? And here's sort of one example where you can see very clearly the distinction. So if you set up systems where you have an alternative kind of understanding of the number of like the bits you think it's using, and then you look at in the learning process how some parameters are behaving, you can see the gap between the two. Okay, so I'll briefly sketch the setting. So this is based on joint work with James Clift, James Waldridge, and Tom Waring. So you can consider, that's a particular example. I think the general idea is something that's sort of adjacent to many things we've discussed here, which is take some classical computational model, whether it's Turing machines or circuits, try and embed that into a smooth relaxation where the original discrete objects are sort of points in a continuous parameter space, and try and cook up a singular learning theory model such that the KL divergence has as zeros the original objects. So, yeah, I think, well, I'll continue that on the next slide, but let me set up this particular example. So a smooth relaxation of this particular system, universal Turing machine. So universal Turing machine is a gadget that looks like this. You don't have to set it up this way, but you can set it up with 3 tapes, a code tape, a work tape, and a state tape. The code tape has entries, which are symbols from the finite alphabet specifying which Turing machine, which algorithm to execute. You put on the work tape some input that you want the UTM to simulate this Turing machine on. You give it some initial state, UTM chugs away, it then has on the work tape the output, and that's what you send back to the person who wanted to execute this code. Okay, so that's a UTM, one particular UTM. Now, a smooth relaxation of that can be constructed as soon as you have a way of propagating uncertainty on any of these tapes through these steps. You can do that a number of ways, some trivial, some not. I won't tell you how we do it in particular, but it's non-trivial. So think about this as a sequence of probability distributions, say over zeros and ones. So you're sort of uncertain about which bit is on the code tape. And then you propagate that uncertainty in a particular way under sort of slightly strange conditional independence hypothesis. That gives you some distributions on the tape. There's no uncertainty about the input, no uncertainty about the state, but there's some uncertainty about which code you're executing. That uncertainty propagates until it's potentially on all these tapes. You look at the work tape and then you say, well, so you can view this now as an inference problem, right? Suppose you know the machine you want. Well, you don't know the machine, you know what you want it to do. You know a specification. Maybe that's a bunch of input-output pairs. So for every of the input-output pairs in your true distribution, you put the input X on the tape. You think of this as varying over all possible codes. You push it through, you get some distribution on the work tape, and you compare that distribution to the correct sequence that you want as the output, say by a cross entropy. And then that gives you a loss, which is the KL divergence of some SLT triple. And that loss has as its local minima, in fact, global minima, certain codes. Among those are the discrete codes, which are actual honest-to-God Turing machines, which solve your problem, but there may be other ones that are sort of have some uncertainty in their tapes. Okay, so that's how you set up the UTM and synthesis problems and put that into the context of SLT. So why am I telling you that? Well, this is what it looks like. If W is your parameter space, so that's the space of codes with uncertainty. That's a manifold with corners. The vertices stand for the classical codes, and this green is meant to be the Bayesian posterior of this problem. So this is a synthesis problem for which this corner is an actual Turing machine, which is a solution. And if you sampled from some initial distribution here, Markov chain Monte Carlo or SGD or whatever would make its way down here. Yeah.
I don't know if this gets too much into the nitty-gritty, I guess, but can you view exactly how the uncertainty propagates as like taking a convex combo of like different codes essentially on the
I can tell you exactly how it works. Yeah. So the way it works is, so you've got a bunch of uncertain bits here. The UTM, while it's simulating the machine, if you remember, if you've sort of seen how a UTM, like if you write the tuples for a UTM, it has some tuples that say, okay, look at this symbol on the tape and look at the current state of the simulated machine, and go to the tuples down here, search for the one which is referencing that state and that symbol, read off what I should do, then go do it. Okay, so the UTM is constantly querying the bits or the distributions over bits that are on this tape. The way you propagate uncertainty here is every time you look, every time the UTM looks, it takes an independent sample, which is very strange, right? It's like you're uncertain about what the bit is, but like that means you should sample it once and like that's what you use, right? And use it multiple times. But like you're uncertain in a way where you just keep sampling. If you use that bit 3 times, you take 3 independent samples from that distribution. Yeah.
Is this part of the connection to linear logic, like the linear bit that you can only use it once?
Yeah, exactly. So this particular way of propagating uncertainty comes from encoding this UTM into linear logic and taking the semantics of linear logic. That's like a very roundabout way of coming up with this very simple way of propagating uncertainty, but it's fundamentally rooted basically in switching from classical logic to linear logic, where copying is actually something that you don't get to, like, taking the sample once and using it twice is sort of like not allowed, because you sort of have to spend something in order for those two things to be equal. Anyway, that's sort of a different topic, but it's like some linear logic way of thinking about why that's reasonable. Yeah, but you don't have to believe in that necessarily, because at this level, all I'm sort of saying is that if you come up with some way of propagating uncertainty, then you can play this game of embedding it. And this is one particular way that's sort of well justified, in the sense the gradients you get are logically meaningful. Okay, so how does this fit into the RLCT story? Well, the classical codes that solve your problem are vertices on that square. So you can take that corner and you can compute its RLCT. And that's upper bounded by the number of bits that actually are used in the code. Right, so that would be its length as a Turing machine, but it can be lower. Okay, so here's the place where I have some intuition for why the RLCT is lower than just the sum of factors of a half times the number of normal directions, because it comes from the way in which, like, why does this happen in practice? Well, here's the reason. So the variables in this model parameterize probability distributions over the code tape, with each group of variables describing like some possible square on the code tape. So it might be, for example, what the Turing machine should do if it sees an X on the work tape and it's in state move to the right. Then it should do something or other. And that something or other is parameterized by a point in a manifold, which is the space of probability distributions that it could be doing. And that's one of the UIs. Okay, so the things on the code tape are, you can think of them as parameterized by the UIs. Bits on the tape, on the code tape, which are used more often. So there's, like, in a program, some variables are used very often, some not very often, right? So there's like a hierarchy of use. The ones that are used more often end up with higher powers in the KL divergence as a polynomial, just because of this independent sampling business.
Is the power the number of uses?
Not exactly, no. Yeah, so this is like an intuition. In some cases, like, it literally tells you the RLCT, but that's not a general thing. Okay, so the higher the degree with which a variable appears, generically speaking, the lower the RLCT will be. Remember, x to the n gives you 1 over n. So higher degree implies lower RLCT. And bits that are used more often by a code are cheaper. They contribute less to the learning coefficient. They contribute less to this cost of bits of improving your parameter, right? So all else being equal, you'd rather use one bit many times than spread computation over multiple bits. Yeah.
Can you elaborate the last point a little bit more?
Yeah, sure. Okay, so on the earlier slide, I gave an example where the learning coefficient of x to the n plus 1 plus y squared plus z squared was a term for the x to the n plus 1, which is 1 over n plus 1, plus a half for the y squared and a half for the z squared.
Yeah.
So if you imagine this is a sum of a bunch of powers of UIs, right, the UIs that appear with high powers will contribute to the learning coefficient with 1 over a high power. Okay, now the way this doesn't translate directly to neural networks, obviously, but if you look at the reason for the polynomials that appear in this equivalent polynomial business from earlier, you can see, well, they come from Taylor expanding the nonlinearity, right? So you can look at the Taylor series expansion of the nonlinearity and think to yourself, why do certain powers in that Taylor series expansion sort of contribute to the equivalent polynomial? And you can sort of have an idea of, like, why maybe certain bits, certain weights sort of maybe effectively get treated as having higher degree and therefore lower RLCT. So that's just kind of a sort of hand-wavy reason for different parameters to be treated differently. Some count for a half, some count for much less. intuitively because they're used more often. Okay. Yeah, let me think. Yeah.
Can you give an intuition for what used more often would, like, if I think about like, okay, single layer
Yeah.
array, what is used more often kind of correspond to?
Yeah, I don't know. You'd have to look very carefully at like Spencer's thesis and the Taylor series expansions. And so I think it's possible to do that. I didn't have time to do the exercise, but yeah. So if you stare at the derivation of the equivalent polynomial, so it's a sum over powers. Powers sort of go up to a number that depends on the number of hidden nodes. And sort of think about it, maybe you could come up with a reason. Yeah, good question. Yeah.
When you say Spencer's thesis, then A, who's Spencer, and B, can you give the 30-second?
Sorry, yeah.
Can you also give like the 30-second?
Sure, yeah. Spencer Wong is a former master's student of mine, wrote a thesis on the relation between the analytic and algebraic in SLT. So this is the story I was telling before. So
Okay.
that's the place to find all the details of one hidden layer 10H. Yeah. I'll post the link. Okay. Just on a slightly different note. Just to tie this back to the story with the free energy formula and internal model selection. I hope that's sufficiently creepy. So I just sort of gave you a picture where there was a model in SLT where different solutions of a synthesis problem were different phases, in fact, right? Different codes give you different points in the parameter space. There are different ways of implementing the same function, right? One function can be implemented by many algorithms. And that's an intuition that's worth having for large neural networks, right? Different implementations of the same thing, maybe different phases with different RLCTs, because different algorithms may use different number of bits or use their bits to. Okay, so that's just a picture worth having in your mind, an analogy between a large neural network with its phases and its RLCTs and a UTM and its set of codes. Right, thank you. More questions? Yeah.
So could you restate your contention in the last section of the talk about RLCT not being related to description length?
It depends what you mean by description length, right? So I guess.
Yeah. So what you said, maybe it's not the right way to put it. So what is the right way to put it?
Yeah. So I actually want to basically escape this slide now. Let me think what I was trying to say when I wrote this. Okay, what I'm actually arguing against here is the intuition that you have a neural network, somehow like you think about the number of bits to specify the weights in it, and that's like in some kind of like if you map that to some kind of classical system, maybe it's like a Boolean network that's very similar to that neural network. And then you sort of count the number of bits used to specify that, and that might be like related to the RLCT. I think this intuition is wrong.
Okay.
That's okay. That probably isn't the right interpretation of description length, right? So maybe there's a better interpretation of description length, which sort of captures the right thing. Yeah. So I guess what I'm saying here is lambda is not what you think the description length is or something.
But isn't the entropy discussion a description length?
Yeah, like kind of, except that it's. But I mean, that's the difference between local and global in a way, right? So like specifying a parameter of neural network, like as in a list of real numbers, is a global specification, right? That's going from, you're going from the whole parameter space, and within that, I mean, giving the decimal expansion is literally decimating the coordinates over and over and over and over. And then there's the parameter. That's like the local, like the global description. But the RLCT quantity, that is like number of bits to specify something, but that's kind of local. So that's the difference between those two. You could think about that plus the bits you need to sort of get into a neighborhood as being a kind of description length. And that's what I was sort of thinking with this MDL related thing. Yeah. So maybe properly understood, that's the right description length. Yeah. I don't know if that answers the question.
Yeah. I have a follow-on question, but I'll come back to it. Who's next? So
So
okay, that's right.
So I guess two questions. So when you say description, like in this sense, are you thinking in the sense of like Kolmogorov complexity or
Yeah,
things like?
something like that.
So I guess to me, it seems obviously false that this connection holds in general for singular models, but it seems like it's possible that for some singular models, there is a connection.
If they use their parameters in a way that's kind of linear, then I would say so, yeah.
Yeah, because I think, yeah, that the kind of description length and the MDL sense or whatever that you get, like you can just derive this from, like it ends up, it's the fact that it occupies more volume and parameter space is what causes it. That like it doesn't leave the system is what is sort of, as opposed to this is sort of it leaves the system because you make some assumptions about.
I'm just sounding a note of caution about, I know people come to this subject knowing like Kolmogorov complexity and all that, and I'm sort of saying that there's a new ingredient because in Kolmogorov complexity, all bits are equal.
Yeah.
Like how you use them matters.
Yeah.
Now, I don't know, like, okay, there's like 3 papers that you could write about exactly what I mean by that. I don't know exactly what I mean. But what I'm pointing to is like, be very careful because
Yes,
there's something going on here which is outside of your conceptual sort of model of what.
yeah, I agree with this. Yeah.
Yeah, just a quick question. So we missed the Mellon transform. Is there a reference that we?
Oh, there's a canonical reference. It's like 300 pages long. No. There is a good standard reference. It's just, I mean, it's not that difficult. It's just like to fit it into 20 minutes, I'd have to just like give you the definition. Like to actually unpack like why these are all reasonable things to do is like 2 hours of like building up to it and then giving you the definitions.
This is a question to both you and Susan. Does Watanabe give any hints as to how we might refine RLCT estimation from the statistician's point of view, like from an experimental point of view? Are there any sort of lines of investigation?
Refine.
Refine.
What do you mean by refine? Like just estimate it in a more scalable way, or
Scalable, more efficient, or
Well,
as in
yes.
efficient as an estimator?
Cares that much about RLCT estimation. I think if you look at his most successful papers, that's probably the WAIC and WBIC papers. And I mean, those are related to the RLCT, but you don't need to know the RLCT to calculate them on your training data. And those are nice information criteria for certain generalization errors. That's probably, I think, one of the least explored, but probably kind of, I would call it low hanging fruit. Just applying WAIC and WBIC to neural networks and using that as a training quantity to predict generalization error. So I've seen work from his students, just in very recent years that continue to look at WAIC and WBIC estimation improvement. But I haven't seen really anything about RLCT estimation out of his group.
one of his students, Imai, has a nice paper looking at a few different variants. So
There's one other paper, I think, that I know.
yeah, thanks.
Yeah, there's someone who did like a WAIC in overparameterized regime and showing that functional variance is still good and valid. Yeah, I can share that.
Can I ask another question? So some bits are not contributing a whole 1/2. An example, it seems to me, would be like when it's contributing a quarter instead, because it was a quartic fit in that direction. So is there some intuition based on the powers? This was also the other example in the, okay, sorry, I've figured out what my question is now. So think of the example where you had the 1 on n plus 1 plus half. And so if you want to say that one of the bits in the code is like the 1 on n plus 1, why is it, what is the interpretation in terms of like a slower variation as you move in that direction in parameter space?
Well, it means it's more important, so it's learned faster, for example.
It's learned faster.
Well, if you look at the gradients of that, it's got an n plus 1 in front of the most important bit. So generically speaking, if you're looking at training dynamics and some bits get fixed very early, then those are probably more important.
But it also seems like it's kind of less important to get it precisely, because in the specification version,
like if x is greater than 1, x to the n plus 1 grows quickly. If x is less than 1, it's very flat. But so there's like the flatness, it's not flat like away from 0. Right?
Okay.
So it's very steep, right?
Okay.
So you flow faster. So it's like when there's something wrong with that bit, it's very quickly learned and then it's flat, but that's not important.
Okay, so I'm focusing on the width of that basin where it is flat, whereas you're focusing on the steepness once you get past the edge of the flat bit. Okay.
Yeah, I mean, it's like, obviously the RLCT is kind of measuring flatness, but if you invert it, then it's sort of talking about the speed of the gradient.
Okay, all right, that's interesting. That's helpful, thanks.
When you invert it, then it's talking about the scale of
the gradients. Yeah, just because I'm just saying the derivative of x to the n plus 1 is n plus 1 times something. So that's going to generically be large.
The speed of the gradient flow will increase, right? Because the time derivative is minus the gradient. So if the FSL in the northern the gradient is large, then you learn very fast.
So it hasn't been systematically studied. There's some like really small example in the derivatives of Turing Machine's paper of that, but yeah.
So Ben, did you have a question?
Yeah, I think I just realized I might ask later.
There was a question of you.
In the speed we're just talking about, that's only a local phenomenon, or is that globally?
Yeah, I mean, in principle, the RLCT is only pick up the local shape. That's right. You had a question?
Yeah, your description as the number of bits used sounds very much like this ETA factor I was talking about this morning. So that's quite interesting. I want to investigate that better. But
one of the unexplained letters in the unexplained ratio.
Right. Well, including the names. But what I wanted to know was, do we know anything about like how canonical these smooth relaxations are? Do you just pick one? Does it not matter? Is it?
We know nothing.
Thank you.
Well, okay. What you can say is that, if you choose this particular smooth relaxation, I can say that the structure of the proof is reflected in the structure of like the gradients and the local geometry. There's plenty more that's arbitrary and to do with your choice, but at least that much is reflected there. So it's not like completely just pick a smooth relaxation out of a hat. You want to choose a smooth relaxation so that the local geometry of the function k that you choose reflects the discrete structure that you were interested in the first place. That's not an easy constraint to satisfy, and this is the only, I think, the only known one that does that. So that's like a non-trivial thing to come up with such a smooth relaxation. So you need to find one like that, and that's a pretty tight constraint, but there will be,
many.
Yeah, you can choose a different encoding of UTMs and you'll get a different one.
Right. Well, what if okay, I'll ask it.
Yeah.
So in this case, we can engineer that relaxation.
Yeah.
For neural networks, it's given to us.
Yeah.
Is that an important distinction?
Well, I'm not actually saying that, this linear logic thing is not actually really you're not meant to think of it as telling you anything about neural networks. It's giving you a system in which you can really justify the intuition that I was trying to express. And then it's a question mark whether that intuition holds for neural networks. I'm not saying anything more than that. I don't assert any connection between these things and neural networks, but it's like an example of, since a lot of people here sort of seem to be curious about bridging the sort of classical theoretical computer science world with discrete things and things that sit inside continuous parameter spaces and are learned by gradient descent. This is one of the very few principled ways of making that connection. So, of course, there are others. That's the only one that's sort of singular learning theory native, as far as I know. Okay. Shall we stop there? Thanks, everyone. Cheaper. Yeah. Don't worry.
I see, yeah. Well, it might have to do with more like the T frequency, but I'm not sure.
I'd be interested if you can see something like that.
But what's funny actually was I realized that I'm pretty sure that this gives you a basenet. Because like each time the code, like, so first of all, there's the normal connection between a QTM and a drawing machine and a basenet. Not a basenet, drawing machine and a Boolean circuit. And the Boolean circuit, the first there actually, like, you can, when you use a code, you can basically turn that into a Boolean circuit, because it's like every time you use it, the fact that you have to do this, and it's something that's necessary.